Friends, this lesson is on section 3.3, coefficient of determination. It's going to use a note packet that looks like this and also an Excel spreadsheet that looks like this. Both of them are posted on Brightspace. So this is as much a topic in statistics as in modeling, but for our purposes, remember that chapter 3 is on so-called empirical models. And that's the case when we don't have an idea ahead of time what specific form of model we should use. We don't know whether it's quadratic or exponential or whatever. So we look at the data itself and say, oh, I think it looks like this, and go ahead and try that form of model. But because somebody else could have said, I'm going to try another kind of model, we want some way of evaluating how well a model fits the points. And the coefficient of determination, or R squared, is one such measure of goodness of fit. It's not the only measure, but it's one such measure. So here's going to be the theory context. We have a bunch of data points, x1, y1, x2, y2, and so on. Let's let y bar be the mean of all of the y coordinates, the mean of the values of the dependent variable. And then we're going to, in this case, fit a linear model, y equals beta 0 plus beta 1 times x. So that has a line for a graph. And then when I take an x value and plug it into my model, I will generate a y value, and I'm going to call that y hat to distinguish it from y, which is an actual coordinate. So here on the picture, a bunch of red data points, and as we said, we're going to take the mean of all of the y coordinates. So that is happening on the line here. So that's what we said we're going to call y bar. And then the actual values will be denoted just plain y. So for this dot here, which is the one we're focusing on for the moment, this vertical coordinate is what I would call y. And then here's my regression line. So if I take the x value for this data point and plug it into the regression equation, as we said, I'm going up here, plugging in right here is the y coordinate that my model generates. And so we call that y hat. So notice that these three values are three different numbers in general. And then let's start talking about the difference between these three values. So one of them is right here. This is y minus y hat. And what we're going to say about that is that's the unexplained deviation. So the regression line is trying to explain or predict the y value of a data point. So it guessed here, but the actual point is up here. The model wasn't able to explain this difference here. So unexplained deviation, or in statistics called a residual. This distance right here is y hat minus y bar, and it's the part of the variation that the model can explain. And then this here is the so-called total deviation. It's y minus y bar. So let me give an example. If, heaven forbid, I want to predict the weight of your mother, for example, if I don't have any information at all about her, I might guess, okay, 140 pounds. Maybe that's the mean weight of American women. I don't know. If you tell me that, oh, she's 5 feet 6 inches or something, then I would probably choose to generate a model and use that to predict your mom's weight. And part of the difference between 140 pounds and the model prediction, or between your mom's weight, I would be able to explain. But my model isn't perfect either, because your mom's weight is actually here. And so This part I can explain. This part of the variation from the mean I can explain. This part I cannot. And you can just see from the picture here that the total variation is equal to the explained part plus the unexplained part. Now, all of that was happening for just one data point, but I would like my model to work well for all of the data points, to generate accurate predictions for all of the data points. So now let's start talking about what's happening in totality. If I take the total part, the y minus the y bar, that's this big distance, and square it, and then add those squares for each of the data points all together. So this data point had a different y and y hat, and this data point had a different y and y hat, and so on. If I square and add those things together, we'll call that the sum of the squares of the total variation. Then if I do the same thing for the residuals, the unexplained deviation, call that the sum of the squares of the residuals. And finally, the explained deviation or regression term, square and add, and call that the sum of the squares of the regression. You've seen before this idea of squaring individual results and adding them together a lot. So I don't just want to add the deviations themselves together, because some of them are positive and some are negative, and they tend to cancel each other out. I might think about taking an absolute value, but maybe I want to do some calculus techniques, and absolute value and derivatives don't work well together. And so the next idea that comes to mind is squaring, and this is very, very common in mathematics, not just in modeling. So sanity check. Here are 3 pictures, and for each picture the question is SS residual a large or a small number, and is SS regression a large or a small number? Before we get into that, let's draw the means. In this case, the mean y is probably something like this, and maybe similarly here, if I try to draw through the middle, maybe y bar is about there, and in this picture, y bar is about there. So similar means for all of them. And then if I draw the regression line like this, for the first picture, the regression line is going to be basically flat, just right across here. For the second one, the regression line is something like this. And the third one, who knows, it's hard to say, but maybe mathematically it ends up being something like this. Now, back to case 1. Is SS residual large or small? So SS residual is measuring the deviation between the actual values and the predictions. So that's vertical distance between the black dots and the blue regression line. Those are individually small, and so when I square them and add together, I get a small number. How about SS regression? That's measuring the distance between the regression output, so the blue line, and the overall mean, which was the green line we drew earlier. That's also a small number. So both of these are small, and we'll talk in a moment about what that means, but notice in this case that really no model is needed. If I want to predict y, I can just use y bar because the values aren't deviating much from those at all, so why go to any work to do anything? Case number 2, back to SS residual, difference between the actual values and the predicted values, so difference between black and blue here, those are small, so SS residual ends up being small. And SS regression, that's difference between the predicted values blue and the mean value green. So for a lot of these points, that's getting to be a pretty big number, and so this is large. And here's a case, of course, when I don't just want to use the green line for the mean. If I'm trying to predict the black the location of the black dots, I'm much better off using the blue model. So here's a good place for modeling. And in the third situation, SS residual, difference between the black dots and the blue line, regression line, those are large. And some of the squares of the regression, difference between the blue predicted values and the green line for the mean, those are also large. And notice here, there's not much to be done. These points are basically in a random pattern, and so asking to fit a line to these points is kind of a lost cause. So no good model possible. And so it was case number 2 where there was a good model fit. So now we'd like to make a measure that is large or indicates that this kind of situation is a good model, whereas these maybe not so good. It can be shown that SS total is equal to SS regression plus SS residual. That's saying on the whole, this equation that was true for one data point is actually true once I do all the squaring and adding. That seems intuitive, but it's actually not trivial to prove. We won't do that. Just take it for what it's worth. And now we're going to define the R squared to be SS regression divided by SS total. And let's answer some concept questions here. What's the range of values that R squared could take? Well, since SS residual is greater than 0, it's the sum of the squares of some things, then if I come up to this equation and say, well, this guy is going to be a non-negative term, then we can say something about the relative values of SS regression and SS total. Specifically, SS total is SS regression plus something non-negative. So SS total has got to be greater than or equal to SS regression. Now, let's take this compound inequality and divide through by SS total. So 0 divided by SS total is just 0. SS regression divided by SS total is R squared. And SS total divided by SS total is 1. And so we have it. R squared is going to be a number between 0 and 1. Well, let's go on to number 2. What does the number R squared tell us? SS regression was how much of the variation the model could predict. SS total was how much variation there was. And so this is a fraction that can be predicted. So this is the proportion of variation in Y that can be explained or predicted by the variation in X. And that makes it a way to compare models. So I build a model, I compute my R squared. You build a model, you compute your R squared, and then we compare R squared and say that, oh, for example, your model explains more of the variation than mine does. So in that sense, it's a better model. So one way to compare models. And third concept question, how is the value of R squared affected by the units of the data? So suppose I measure weights in pounds, for example, people's weights in pounds. And then I go to Canada and they say, no, we want to measure weights in kilograms. And so I do my data conversion, but what does that do then to the r squared if I'm comparing weights and heights? Well, if we come here, if we change units of measurement for y, for example, if we change from, let's take an easier example, we change from yards to feet, which would multiply all the y values by 3, then SS total is going to get multiplied by 9. But so is SS residual and SS regression. They would also get multiplied by 9. And then when I do the division, the factor of 9 will cancel out again. So since changing units changes SS regression and SS total the same way, R squared doesn't depend on units at all, which is a wonderful result. It's hard to overestimate how good of news that is, because usually for physical quantities, there are a lot of different units of measurement that we could have, and we're saying it doesn't matter. This is measuring something inherent about the data itself rather than the way that we measured it. Okay, now let's flip over to this Excel spreadsheet, SS Spring. Remember earlier in the course, we set up a spring, physical spring on a table in class, and somebody, I think it was Chase, actually attached masses to this spring and took measurements of how long the spring stretched. And in columns A and B are the actual measurements that we came up with back in January sometime, I think. So this is a busy worksheet. I'll try and walk through it here and explain what I want to get out of this. So ignore column C for a moment, quite a moment. We'll come back to that. And then in column D, I've basically just copied column B. It'll change after a bit, but at the moment, you can think of the masses here in column A and the amount of stretching in the spring here in column D. So if we were to graph these two columns, it looks like this, and we can see that the relationship between the mass attached and the stretching of the spring is very linear. So it makes all the sense in the world to ask Excel to fit a linear model to this. I'll add a linear fit or a trend line here, and let's display the equation on the chart. So here it is, y equals 0.02558x plus 0.5. And over here, then, I have captured those numbers so that I can use them in the rest of the spreadsheet. On to column E. Now we want to predict the amount of stretching using our linear model. So you can see here, for example, that the column E is generating predicted stretches. It's taking J19, which is the B1, that's the 0.2558 number. It's multiplying it by A3, which is a mass or X value, and then it's adding J18, which is the B0 or constant term. So these values are attempting to predict the stretch values, the actual y's. These are y hats, these are y's, and you can see that because the model is, or because the data is so linear to begin with, the predictions look quite good, actually. But they're not perfect, and so in column F, we're taking the difference between the two. So here are the actual y's minus the predicted y's, and this is the unexplained part. of the variation. Now let's compute the explained part of the variation for each term. That was y bar minus y hat. So I need y bar. That's simply the average of all of the y values, the actual y coordinates. And so here we're taking the actual y coordinates in column D and subtracting, I'm sorry, the y bar, the mean in the cell D14, and then minus the predicted values. And finally, the total variation is y minus y bar, the actual data minus the mean. So a formula like this is taking values from column D, the actual value, minus cell D14, the mean. And if you look across a row, it should be the case and is the case that the unexplained variation plus the explained variation equals the total variation. Now let's take each of these guys and square them. So in column F, I have the unexplained variation. I square those, and if I add the squares together, so here is the sum of column I. If I add these squares together, this is the sum of the squares of the errors, or sum of the squares of the I'm using a different notation, sum of the squares of regression. And here is y bar minus y hat. I'm taking the square of y bar minus y hat, square of column G. I add those together and add, and this is the sum of the squares of the regression. And finally, column K is the square of column H, which is the actual value minus the mean. And if I add those squares, I get sum of squares total. So again, here in column I are the values that are generating SS residual. Here is SS regression, and here is SS total. So now, per the formula for R squared, I take SS regression and divide by SS total to get the R squared. We said that this number was going to be between 0 and 1, and because these data points are so close to linear, R squared is a very high number, 0.999, basically, telling me that the regression equation can explain almost all of the variation in stretch distances here. Let's see, something else we can do is to come to the model and click on the regression line. And before, I displayed the equation on the chart, so you may know that Excel can also calculate and display the y squared. And so there it is. Let's drag this off the line a little bit. So there it is, 0.9986. So that would have been a far easier way to get the R squared, but I wanted to go through all of this to show you where it comes from and that it really works. And so we have a model that is almost a perfect predictor. So I won't write down these numbers, but we've done parts 1 and 2. And part 3 says, then let's add some noise to the actual spring distances. Okay, so what's going on here? In real life, you almost never are able to perfectly capture data. Your instruments may be inaccurate, for example. So that could be part of why we choose a model with some added noise to model the inaccuracy, in fact. Or there are other factors going on as well that aren't built into my model. So if I'm using weight to predict height, for example, weight is a fairly good predictor of height in a person, but there are other factors as well. Gender and age and other variables that I could use to predict height. And so adding some noise is a way of generating or testing how well the model does given that other possible predictors are out there that are not being accounted for. Okay, let's see what happens now when we go here and start cranking up the noise. Go back to column C. What it's actually doing, if I look at one of the formulas, is generating a random number and then plugging it into normal inverse. So this is generating a random data according to a bell curve with mean 0 and standard deviation sigma coming from this cell. When you model noise this way, you usually assume that the mean is 0 because you have no idea whether your actual values are too large or too small. Probably some of them are too large, others are too small. So you usually use a mean of 0, and then the standard deviation has to be a positive number. Right now it's set to 10 to the negative 9, which is so small that it's not doing anything. That in column D, when I'm adding the actual value to the noise, I'm just basically getting the actual value. But now, when we start cranking up the standard deviation of the random variable, the bell curve random variable, these numbers in column C are going to start to get larger, and they're going to mess up the actual stretch values. So here's 10 to the negative 9. Let's try 10 to the negative 6. So I delete 3 zeros and push enter, and you don't notice any effect at all. The r squared is still the same. The numbers are basically the same. I guess in the very least significant digit, now you're starting to see just a little bit of noise variation. Let's crank up the noise some more. How about we go to 1/1000th? And you can't really tell any difference on the graph. The r squared is the same to 4 significant digits. In the column D, you can see just a little bit of deviation now from column B. Let's crank it up some more. How about 0.1? And still, you can't see any difference in the graph. The r squared, maybe it's changed in the 4th decimal place or so. Still not doing much. The stretch and the noise are vastly different in scale. The stretch is much bigger than the noise. Let's try 1. And now we're starting to see the r squared drop just a little bit, but it's still 0.998, and I can't see much difference in the graph. Well, how about r squared equals 10? Oh, okay. Now you can visually see in the graph that the data points are starting to scatter. They're not linear anymore once the noise has been added in, and r squared has been cut to 0.96. I can